Next, we will discuss the voltage regulation. So it is clear that with change in load, there is a change in terminal voltage of an alternator. The magnitude of this change depends not only on the load but also on the load power factor. So the voltage regulation of an alternator is defined as the rise in voltage when full load is removed, field excitation and speed remaining the same divided by the rated terminal voltage. Therefore, the voltage regulation is equal to no load voltage minus terminal voltage divided by the terminal voltage times 100%. So note, EO minus V is the arithmetical difference and not the vectorial one. So we will not consider their directions, only the magnitudes. In the case of leading power factor, leading load power factor, terminal voltage will fall on removing the full load. Hence, regulation is negative in that case. So in a leading power factor, our terminal voltage will increase versus in its original rated terminal voltage. So pag leading power factor or capacitive yung load mo, that example, the terminal voltage of your alternator is 230 volts, and if you connect a capacitive load, of course it will increase from 230 to up 230, magi-increase yan. So let's say 240 volts. So what will happen is magiging negative yung voltage regulation mo. The rise in voltage when full load is thrown off, it is not the same as the fall in voltage when full load is applied. The voltage characteristic of an alternator are shown in figure 37.9. So pag lagging power factor naman yung load mo, it will fall. So magiging less yung terminal voltage mo versus dun sa rated terminal voltage. So the percent regulation will be positive. Okay? So unity, yun lang yun. Determination of voltage regulation. In the case of small machines, the regulation may be found by direct loading. The procedure is as follows. The alternator is driven at synchronous speed and the terminal voltage is adjusted to its rated value. The load is varied until the wattmeter and ammeter connected for the purpose indicate the rated values at desired power factor. Then the entire load is thrown off while the speed and field excitation are kept constant. The open circuit or no load voltage is red. Hence, regulation can be found from percent regulation is equal to EO or E0 minus terminal voltage divided by terminal voltage times 100. In the case of large machines, the cost of finding the regulation by direct loading becomes prohibitive. Hence, other indirect methods are used as discussed below. It will be found that all these methods differ chiefly in the way the no-load voltage EO is found in each case. So these are the steps or methods in finding the percent regulation of large machines. We have the synchronous impedance or EMF method. It is due to Ben Eschenberg. Synchronous impedance or EMF method. The ampere turn or MMF method. This method is due to Rother. Zero power factor or Pocher method. As the name indicates, it is due to Pocher. All these methods require armature or stator resistance RA, open circuit or no load characteristic, short circuit characteristic, but zero power factor lagging characteristic for poacher method. So now let us take up each of these methods one by one. So value of RA. Armature resistance per phase can be measured directly by voltmeter and ammeter method or by using Wheatstone bridge. However, under working conditions, the effective value of RA is increased due to skin effect of a conductor. The value of RA so obtained is increased by 60% or so to allow for this effect. Generally, a value of 1.6 times the DC value is taken. OC characteristics, open circuit characteristic. As in DC machines, this is plotted by running the machine on no load and by noting the values of induced voltage and field excitation. It is just like the BH curve. So we will discuss this further mamaya. SC characteristic, it is obtained by short-circuiting the armature such that stator windings through a low resistance ammeter, the excitation is so adjusted to give 1.5 to 2 times the value of full load current. During this test, the speed, which is not necessarily synchronous, is kept constant. Example number 1, we have the effective resistance of a 2200 volts, 50 Hz for 140 kVA single phase alternator is 0.5 ohm. On short circuit, a field current of 40 amperes gives the full load current of 200 amperes. The electromotive force on open circuits with the same field excitation is 1160 volts. Calculate the synchronous impedance and reactance. So we will calculate the ZS, synchronous impedance, that is equal to our 1160 volts divided by 200 amperes. So that is equal to 5.8 ohm. Using the impedance triangle, calculating the XS or synchronous reactance, that is square root of ZS squared minus RA squared, that is square root of 5.8 squared minus 0.5 squared equal to 5.7784 ohms. So that is the value of your synchronous reactance. Example number 2, 60 kVA, 220 volts, 50 Hz, single phase alternator has effective armature resistance of 0.016 ohm and an armature leakage reactance of 0.07 ohm. Compute the voltage induced in the armature when the alternator is delivering rated current at a load power factor of unity, 0.7 lagging and 0.7 leading. So we will compute the induced EMF or the E. Okay? Given our apparent power for our alternator is 60 kVA. Its voltage rating is 220. Armature resistance 0.016 ohm. Inductive reactance is 0.7 ohm. So required the value of your induced EMF at unity, at 0.7 lagging, and at 0.7 leading. So first, before computing all this 1E, kailangan muna natin yung current. We can compute current equal to our apparent power divided by the voltage. So 60K divided by 220, that is 272.727 ampere. For the first one, unity power factor, we have this vector diagram that the voltage and current are in phase. Okay? So based on this vector diagram, we can compute your E by the vector sum of V plus the drop in your IRA and the drop in your IXL. Our working equation now will be based from this vector diagram, our E is equal to the vector sum of V plus I times RA plus XL. So, same lang yung current. IRA drop is 272.727 times 0.016 equal to 4.364 volts. So for IXL, equal to 272.727 multiplied by 0.07 equal to 19.091 volts. You can simply calculate E by Pythagorean theorem for the magnitude only. So if you want to get the magnitude and the direction, you can use polar form. Or E is equal to 220 angle 0 plus 4.364 angle 0. So this angle 0 kasi they are in phase with the IRA and the voltage and the current are in phase, kaya angle 0. Plus 19.091, this one, angle 90. Ito, angle 90. So you will get the magnitude and direction. If you will use Pythagorean theorem, you will only get the magnitude. So E is equal to 225.175 angle 4.864 volts. This 4.864 is the angle between our reference and the induced EMF. Next, for lagging power factor or lagging, we have 0.7 lagging, or the angle theta is equal to our cosine of 0.7. That is 45.573 degrees. So this is lagging. Our current now will be placed here, lagging with respect to the voltage. So this is our voltage in the reference. We will plot the IRA. So it is in phase with I. Nandito siya. IRA, and our IXL is 90 degrees with respect to IRA. So we can calculate E is equal to the vector sum of V plus your IZ. You can calculate IZ by IRA plus IXL. So your impedance, this one impedance, is equal to the value of your resistance and the value of your inductive reactance. The 0.016 plus J 0.07. So I will use V plus vectorially sum of IZ. So 220 angle 0. So angle 0 yung voltage. Plus the product of your IZ. What is I? 272.727 angle. What is the angle? That is negative kasi lagging. Negative 45.573 times your Z is 0.016 plus J 0.07. So if you add the 220 and the Z, the V and the IZ, you will get the magnitude and the direction. 236.91 angle 2.479 volts. You can also solve E by cosine law. Kung gusto nyong mag-cosine law, sine law, pwede rin. So, pwede nyong kunin muna tong IZ and then get the angle here. Okay, and perform the cosine law. But for me, it is easier kung ganito. For leading naman,